Hey guys, the objective of this video is a brief introduction to dead and live load, which is AS1170.1. So this is the dead and live load component of the course. We're going to be looking at the procedure going from pressure to line to point load, which is a very essential understanding, which we need to grasp our heads around. And then we need to look at the units used in the code and units used in this course. So the first thing we're going to be looking at is the dead load, G section 2. So if I show you, we're in AS1170.1, so part 1, permanent actions and other actions. If we go over to section 2, we've got in the code stuff about the permanent actions. Now this section is only one page. If I flip over, we're in section 3 straight away, imposed actions. Now this part of the course, working out dead and live load, is actually the least standard intensive. So what I mean by that is that we refer very little to the standard throughout this part of the course compared to other topics. Especially the dead load, it becomes a lot more intuitive to work it out. So if I just show you basically what we're doing, we have the dead load, which is the addition of the self weight and the superimposed dead load. So we saw this in the previous video. So dealing with the self weight first. We're going to have, say, a slab, and we want to work out the point load. Okay, so how do we do this? The basic procedure is the self-weight of this slab is its mass times its gravity, okay, which is a force. So looking at the units, we have kilograms times meter per second squared equals kilogram meters per second squared, which is a Newton, okay? Now, normally we don't know the mass of a slab. So we have a huge slab in a building, we can't use a scale to weigh this slab. It's not practical. What we do know and what we can work out is definitely the volume of the slab. We can work that out, and we would know the density based on its material properties. So we're going to use this relationship here, density equals mass on volume. Rearranging that to get mass equals density times volume. We can substitute that back into that equation there, which means we have equal to density times volume times gravity, okay? And unit-wise, we get back to Newton. So kilograms on meter cubed by meter cubed, they cancel out, giving us kilograms times meter on second squared, kilogram meter on second squared, which is a Newton. Okay, so we can say that the self-weight of this slab is rho, the density, times v, the volume, times g, gravity, which gives us a point load in newtons, okay? But throughout this course, we're not really going to be using this procedure because we want to normally go from the self-weight, we want to look at it as a linear load, okay? So we saw over here, we found the slab as a point load, but what we normally want to know is the slab, say, as a linear load. And the reason is because we're going to have a beam underneath this slab, and we want to know the linear load in this beam from the slab, okay? So the way we do this is we go density times by the area times by gravity, okay? So instead of the volume now, we'll multiply by an area. And to know what area it is it h times b? Is it b times d? What lengths are we using to find that area? We exclude the length of the direction you want the load in. Okay, so what I mean is this. It's very important to get your head around this because it's a very essential concept. We want our linear load going the same direction as the beam. So we want the load parallel to this beam. So the dimension or the length we leave out is that dimension. So in this case it's d, okay? So you can see that d is parallel to the load. So in order to work out this linear load, we leave out d. So we're going to go rho times h times b times gravity, okay? Let me repeat that again. To work out the linear load, you times it by the area, and the dimensions you multiply it by are you multiply by the ones which aren't in the same direction as it. So in other words, you just exclude the dimension parallel to the linear load. So we multiply by h and b times gravity. Unit-wise, we would get kilograms meters second squared on meters, which is a Newton per meter, say, which is a linear load, okay? So we can see rho times h times b times g. This gives us a UDL, okay? It might not seem so intuitive why you exclude that length, but if you exclude that length, it gives us the UDL in that direction. If we were to, say, multiply by h by d, we would have a UDL going in the opposite direction. So we would have a UDL like this. I'm drawing very light pencil, but the UDL would be going in this direction, along that edge there, not along that edge. Okay, so just exclude the length of the direction you want the load to go in. So normally we're going to be using this type of procedure, density times h times b times gravity, where you just have to know which way the load's going in, and you're going to have to identify what h and b are for your particular problem. We're going to get a UDL, okay? Now, the superimposed dead load is going to give us, we're going to be given a pressure normally. So we're going to say a carpet, say, has a pressure of 1 kPa, okay? So we want to be going from a pressure to a linear load. So all we do is we go, the G superimposed load is the pressure times by the perpendicular length. And it's the same type of idea here. If we want the load to be going, if we want the linear load to be going in this direction, we multiply by the one perpendicular. So we multiply by B. So in other words, we're excluding D, okay? So if we want the, once again, if we want the linear load going in this direction, we multiply the pressure by the length perpendicular to that load. So we're always excluding the one we always exclude the one we want the load to go in that direction, if that makes sense. So in other words, we're going to go pressure times B. A pressure normally is kPa or something like that, so it's kilonewtons per meter squared is a pressure load times by a length meter would give us kilonewtons per meter, say, of that UDL. The next one is the live load. Now the live load is it's the exact same process for this superimposed. We're going to be given a pressure. So if I show you, this is in section 3. So it's on just over the page. We have things about imposed actions. And what we're normally going to be referring to is a table. So table 3.1, for example, has reference values of imposed floor action. So let me zoom in for you. So we're given, say, office and work areas not covered elsewhere, for example. Operating theaters, x-ray rooms, utility rooms. We're given a pressure of 3 kPa. Okay? So the code tells us that we need to apply a 3 kPa pressure in that situation. Let me just zoom back out. Okay, so a pressure will be given to us based on a table, and it's the exact same procedure. We want to go from a pressure to a linear load. We're just going to go pressure times the perpendicular length to the load. So pressure times B will give us kilonewtons per meter, say. Okay, now we need to get our head around this procedure going from pressure to line load to point load. So we've seen now how we go from pressure to line load. So say we have a pressure P, we want to get a UDL. Okay, so to get the UDL, it's pressure times by the length perpendicular to the load, the direction of the load we want it to go in, would give us kilonewtons per meter squared times meter, would give us kilonewtons per meter. Okay, so that is a pressure from a line load. We multiply the pressure by the perpendicular length. Then, we haven't seen this now, but say we have our slab on these columns. Okay, now we want to work out the point load in these columns. So if I show you this picture here, we're now going to be going from the line load to the point load. So here's our UDL. We want to know these point loads on either end of the UDL. Okay, so what we do is we have the point load N is equal to the UDL, which will be in, say, kilonewtons per meter. We multiply that by D, the length parallel to that load. Okay, so we would have seen this in structural mechanics before, this type of thing, where to work out the load, you times the UDL by the length, and then to work out the actual force in each of the columns, we're just going to divide by 2. Okay, and that'll give us the axial or the point load in each column. Kilonewtons per meter times by meter gives us kilonewtons. Okay, so I just want to introduce this type of procedure because this is the foundation of this entire topic, is being able to identify the process going from, say, pressures to line loads to point loads. Okay, we're going to be doing very comprehensive examples in upcoming videos, but I just want to introduce this principle now. The next thing I just want to quickly talk about are units. Okay, in the code, all units are in kilonewtons and meters. Okay, so the first type of unit we have is a Pascal, which is, so we're dealing with pressures now. A Pascal is a Newton per meter squared, a kilopascal is a kilonewtons per meter squared, and a megapascal is a newtons per millimeter squared. Each one of these you multiply by 1,000. So there's 1,000 pascals in a kilopascal, there's 1,000 kilopascals in a megapascal. Okay, now because I said everything's in kilonewtons and meters, we'll either be given in the code, so say table 3.1, we are given stuff in kPa and kilonewtons, because a kPa is a kilonewton per meter squared. Okay, UDLs, an interesting fact, is kilonewtons per meter is the exact same thing as newtons per millimeter. Okay, there's no difference. So in other words, 1,000 kilonewtons per meter is equal to 1,000 newtons per millimeter. Okay, the reason is because you divide the top by 1,000, you divide the bottom by 1,000, they cancel out, so you get back to the same thing. Just on point loads, we either have newtons or kilonewtons. We have 1,000 newtons in 1 kilonewtons. Once again, the code gives us everything in kilonewtons and meters, which is why you'll see values in kPa in the code, because that's kilonewtons per meter squared. Anyway, guys, this is just a very brief introduction to some of the underlying concepts we're going to be seeing for the dead and live load calculations. In the next video, we're going to be doing a very basic example. Sorry, in the video after that, in the next video, we'll be doing a basic example, and we're going to be going through a very, very comprehensive example in this topic. Anyway, guys, hope that helps, and we'll see you in the next video.
Cut study time with concise video summaries by top students. Visit spoonfeedme.com to view more free videos in this course and hundreds of others.